The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you so much, Anna. A very good day to everyone. Welcome to the ITU AI and Machine 5G Challenge webinar session. My name is Thomas Baskol from the ITU, International Telecommunications Union. This is a very interesting day. It's a semi-finale for our challenge. And this specific problem statements on AI/ML in 5G energy consumption modeling is also part of the Green Digital Action Track, which is an ITU-led series of activities at the Conference of Parties, Co-op 28. And the challenge finale, or the final session for the crowdsourcing AI solutions for climate change, will take place on 2nd December in Dubai. I would like to welcome teams that have done well, that have good solutions, that have submitted very good solutions to our problem statements, who will take stage today to pitch their solutions. And I hope by the end of this session, we will have a good idea of who is who and who will be going to COP 28. At this point in time, I would like to welcome our host, Nicola, who has kindly helped us to frame this problem statement, to give us the data set, to give us the support that was needed to make sure that this was a success. So thank you so much, Nicola, for making time and providing resources to make sure that we have this really nice problem statement. Welcome and good afternoon.
Hi, Thomas. Good afternoon. And thank you for introducing this webinar of today. So yes, a few months ago, we have met here to propose this challenge about the energy consumption modeling of a 5G base station, 5G technology, because we believe it is a
You are muted.
I think there is a problem. Can you hear me now?
Yes.
Okay. So we were saying that a few months ago, we have met here to propose this challenge to ITU, as we believe it is important to tackle the problem of energy consumption of 5G. And we believe that machine learning and artificial intelligence are really valid tools that can allow us to solve real-world problems. It is nice to meet here again after a couple of months with many people, in particular with the top participant to this competition. And we have seen a lot of people participating. There were hundreds of participants that submitted hundreds of solutions. Each of them has used the different machine learning tools to solve these problems. And we believe that all these solutions can really help us to have a more sustainable network in the future. And today I'm very curious to see what the top participant created to solve this challenge and the different way they decided to tackle this problem. So before going forward, I would like to take some time to recap the motivation for the people that were not attending the previous webinar, and also the objectives of this challenge. So let me share my screen. So, okay, so today the fifth generation of radio technology is currently being deployed, and this brings new services, new technologies, and new networking paradigms. However, the complexity of these new networks pose new concerns in terms of energy consumption. In particular, the telecom industry is already utilizing around 3% of the globally consumed energy. And this is a problem also in terms of money that the mobile network operators are spending to operate their business. For example, in this slide, we have an example for an European mobile network operator that was spending 90% of their operational expenditure to pay electricity bills. So this is an important problem, not only in terms of money, but also in terms of sustainability of the network. It is even more important if we consider that the energy consumption in the future is expected to increase, and in particular because we are going to have more subscribers. Subscribers are going to have more devices. You can think about all the smart devices that connect directly to the mobile network, for example, smartwatches. And also we will have new services, and in particular services that are data hungry. So they have a large bitrate requirement. So for example, high definition streaming, but also augmented reality and virtual reality. And then also we have entire new verticals. For example, the Industry 4.0 and the Internet of Things. When we dig into this problem, into the energy consumption of the network, we discovered that the radio access network accounts for the largest share of the energy consumption, in particular 73%. And this is the reason why the participants to this challenge were working with data from base station deployments. And the idea, as we have seen in the previous webinar, is that these base stations that are the antenna that you see all around the cities that allow our smartphone to connect to the core network in a wireless fashion, they can be configured with very different parameters. They can have different architectures. There are different products. Luckily, also, we have seen that there are energy-saving modes that allow to reduce their energy consumption. But these energy-saving modes needs to be properly configured. So the first thing to do if you want to optimize this network is to understand how energy is consumed. So how these different parameters, these different architectures, these different products, these different energy-saving modes impact the energy consumption of these base stations. And this was the task that the participant to the challenge had to face. So the objective, we had 3 objectives, but the most important one, of course, was to accurately estimate the energy consumption of a base station, considering the data that we share. So you can see in the input of this box, we have the base station architecture. So we need to understand how number of antenna and specific product, for example, affect the energy consumption. We had many configuration parameters, for example, the number of cells, the bandwidth operated by these, the frequency operated by these cells and their bandwidths. And also we have energy saving activation, so for how long these energy saving modes were activated, and the traffic conditions, so how many resources were allocated by the base station to deliver data to the users. And then we had the two additional objectives. The first was to achieve a generalization across different base station products. This means that in the data, some products were more rare than others, but still we wanted the machine learning solution to be able to provide a rough estimate of the energy consumption of this product, even if they appear in a few occasions in the training data, or if they are not even there, just by generalizing across different products. And objective C was similar. It was to achieve generalization across different configurations. So even if some configuration is not present in the training data, we want to learn the rule that determine the impact between that parameter and the energy consumption. So with this, I leave the floor to Thomas, that is going to share some statistics about the many participants that we had in this challenge. So I leave the floor to you, Thomas.
Thank you so much, Nicola, for introducing this problem statement. So from my side, I will just do a quick overview of the problem statement itself in terms of statistics and maybe some of the things that might be of interest to our participants. So, as I said, this is a Machine 5G challenge, but also is part of the crowdsourcing AI solutions for climate change, which will be a part of the ITU-led Green Digital Action Track. So it's a big deal, I would say. Just a quick overview timeline on how we started. We curate this problem statement around April to June, and we launched at the AI for Good on 6th July. That's when we launched this specific problem statement. So it ran from July, August, September. We closed in September, and now we are doing evaluation. In terms of the award ceremony, the finale itself, the session today, I would like to call it a semi-finale, and the finale will be on 2 December. This is where we are going to give awards, prizes to all teams that has won in this particular problem statement. And I'd like to thank all the hosts of the problem statements. We have several problem statements that are open. You can participate in one or multiple of them. You are welcome to be part of our growing community. And this specific problem statement was hosted by Huawei. Thanks so much, Nicola and colleagues, for hosting this interesting problem statement. And in terms of statistics, we had around 776 total enrolled. And from these, 245 submitted at these are unique submissions. So we had 245 unique submissions, but in total, we had 8,000 total submissions, which is a big deal. Based on Zindi, roughly we have done 2.5 years of work of coding. And I would say that thank you to everyone who put in effort, working so hard to make sure that this is a success. This particular problem statement have covered 83 countries and 30 in Africa. Now, in terms of prizes and awards, the first team will receive cash prize of 5,000 Swiss franc and up to 5,000 CHF covered trip to COP28. Please make sure that you understand up to, okay. And then the runner-up will receive 3,000 Swiss franc, the third 2,000, the fourth and fifth will receive 1,000 Swiss franc. We also have some specific prizes: best solution from students, creative solution, best presentation. These are 1,000 Swiss franc. So we have a total prize pool of about 20,000 Swiss franc, and thanks to Huawei who gave this prize money. Okay, so appreciation to Huawei, ITU, and Zindi for making this a success. And of course, a quick mention, we have a special issue that we are going to announce in roughly about 2 weeks. Please join us, submit your manuscript. And this is an academic journal, so your novelty or uniqueness have to be shown. you have to make sure that you have rigorous literature review. You know how to work on this, but of course we can provide mentorship. If you ask some of us, we can help you to make sure that you submit a good paper for the journal. But of course, you can also reach out to Nicola, who will help you to maybe gather some few teams to make a submission on this special issue. So everyone, please make sure that you submit your solutions. Now, in terms of the session, Nicola has already made a presentation. So we are going to the teams. The format is quick. You have 12 minutes in total, 8 minutes for your presentation, 4 minutes for Q&A. At 7 minutes, I will tell you have 1 minute to finalize. And then at 8 minutes, you stop your presentation and we'll go to question and answer. So right now, I would like to go into the team's presentation. And the first team to present is going to be Li Cheng, who is going to be the first one to present. So these presentations are in random order. So Li Cheng, the floor is yours. You have 8 minutes for your presentation.
Okay, thank you, Thomas. Hello, everyone. I will share my screen. Hello, everyone. I'm Li Cheng Zheng. I'm a PhD candidate from ETS University of Quebec. Now I live in Montreal of Canada. I will first give a brief summary of this computation. So we are required to leverage the machine learning or AI to predict the energy consumption of a base station. The dataset provided contains 3 collections. They are the base station basic information, cell level data, and energy consumption. So we have around 92,000 training items, and we have around 26,000 test items. For each test item, we will have the base station basic information like base station ID, cell number, RU type, mode, frequency, bandwidth, antenna, and the transmission power. For cell level data, we will have the time, base station ID, cell name, load, and the ES mode from 1 to 6. For the training side, we will have the energy consumption, that is the time base station ID and the energy consumption. This would be a label of our training. We are required to predict the energy consumed during some specific hours. And finally, we will evaluate by the WMAPE scores. So I will I will first talk about the data set and what we did on EDA. First, this is the example of the cell level data. We can see for specific base station, it will associate with a different number of cells. For example, the base station 105, it associated with cell 0 and cell 1 during the January 1st at 1 a.m. And also for the different base station, we will associate with different number of cells, of course. So the varying number of cells of each base station at different hours poses the first challenge, that is for deep neural network, because deep neural network always requires some consistent input. So deep neural network cannot be used, at least it's not that efficient in this computation. And besides, I found another thing that is the periodic features of energy. We can see the energy always reached its peak at almost exactly same hours for each day, and the periodic pattern always have a 24-hour circle. This observation led me to consider that the features and energy consumption at the same hours of a day maybe are valuable features we can use for our prediction. And besides, I noticed, the noise issue. I think this is the main challenge. Here is still the energy we plot, but this time we have the hue. This is the number of antenna and the bandwidth. We can see when we take the number of antenna and the bandwidth out with different number, we will see the periodic is still there. We can see it's still going peak like this curve, but it's not that perfect. I think this is because, the energy data exhibits some noise because of some noise. This can be a negative impact on the decision tree algorithm, like LightGBM. In order to answer why, I will first introduce how LightGBM works. This algorithm is on decision tree. They are iterative solution. They are adjusted their sample weights based on the prediction from previous iterations. Consequently, as the iteration progress, the error tend to be decreased, leading to a reduction of mode of bias. This is how do we do in such a tree iteration, but in our problem, there would be some significant noise. minimize the best. Sometimes we are trying to minimize is not what the expected value. Instead, we are minimize our distance from noise. We know noise always some random value, so this would be a challenge for us. Before solving this issue, I will first talk about the feature engineering. We will have three sets of features. The first feature is the basic features we have. That is the 11 features we are given, but I combine them with different cells like cell 0, cell 1, cell 2, and cell 3. So overall, we will have the 44 features. These are the basic features we have, and these are also a part of our basic inputs. Besides, as I mentioned, there are some periodic features. So what I do for feature side 2 are periodic things. We will have the energy and the features of the past 5 days in the same hour. For example, if we want to get we want to predict the 5 a.m. The energy consumed, what we do is we use like the Thursday, Wednesday, Tuesday, and Monday as another input. That is the energy, that is the previous day's energy. And we also have the feature of past 6 days at the same hour. Besides, we will also have the difference of the features of the past 6 days. That means what is the difference of the features in previous day and the 1 day before until the 6 days. And also we have the percentage of the features in past 6 days. The 5 day and 6 day are what we get is from experiment. We found the energy from past 5 days, feature from 6 days, difference and percentage of 6 days would be the best features. Also, it is possible like we only have the data from January 1st to several days. Maybe we want to predict the January 1st data. At that time, yes, the past 5 days data would be leave on the blank. From now, we will call the first feature energy of past 5 days as the previous energy, and the percentage of the features of past 6 days, we will use it, we will call it as the percentage of features. Another feature set is the difference and the product of features. This idea comes from the introduction of a web seminar from Dr. Nicola. He mentioned that the features, the load is a percentage we used for the base station. So I think it maybe have some relationship with other features like the frequency, because the load is between 0 and 1 is the percentage. So, but the frequency and the bandwidth, it is base station itself property. So what we do is we will see the relationship between them. So we tried the difference, product, division, and the summation of different features. Finally, difference and product would increase the score. So we will use the difference and product of different features as our another input, because ES mode always contains 0. So, and we tried it didn't increase score, so we simply use the difference product of these features. And the feature site 3 and the feature site 1, we will combine them together as our basic inputs. So let's talk about the models we are using. As I mentioned before, the most challenge would be noise problem. So we propose an idea that is the residual light GBM. The residual light
finish.
Okay, a bit fast. The residual light GBM contains two light GBM structure. The first light GBM will contain the basic inputs and percentage features. And then based on these hints, the light GBM1 will predict the energy consumption. And after it, the energy consumption and the basic inputs and the previous energy will be sent to the light GBM2 and to predict the energy consumption. Because of the residual prediction as the input, the basic information are input twice, so it can alleviate the impact of noise. So this is our idea. So this is our baseline, 2 baselines to predict the effectiveness of our solution. So we will compare it with the light GBM with the 3 inputs together. We also exchange the previous energy and percentage of features. We exchange them to see the performance. Finally, we did some submission. The first submission is about the features we add. We want to see what is the progress of it. We can see with the light GBM, the basic feature can get 0.12 with the public and private score. But if we add some new features, we can increase to 0.11. And we also try to see the difference, the submission scores of different methods, like light GBM, we can get 0.0993 and 0.092 respectively on public score and private score. Like GBM the residual, or like GBM2 can get, it's close, but it's still worse than that. So in this competition, we propose the right residual like GBM to solve the noise problem. Finally, we also did some data processing and feature engineering. Finally, we got a 0.093 for public score and 0.092 for private score. For future work, we tried the RU type and the mode. We didn't use it for our final input because they cannot increase our score. It decreases our score. So in the future, we will try to explore more methods on how to use these two features. And also maybe the deeper residual like GBM, maybe 3 or 4 layer may be helpful. We can try it later. So this is my solution. If you have any questions.
Thank you so much. I would like to go into the Q&A. So Nicola and Vishnu, please, the floor is yours.
So if I can, I would like to ask a question to Li Sheng. So first of all, thank you for your nice presentation. I've seen that you use measurements collected in the previous hours to have higher accuracy. And in your slide, if I'm not wrong, you say that you use measurements collected in the previous 5 or 6 hours as an input. So I would like to ask you if you have analyzed how the different numbers of previous days you input affect the accuracy. So you have decided to use a 5 or 6. Have you tried with more or less? How is this the selection of the number of days affecting the accuracy?
Okay. Yes, we tried for like the energy. We tried it from past 1 days and until past 5 days until past 7 days because the length is always collected in 7 days. For everything we tried from the 1 day it is increasing until the past like energy until the past 5 days. It is still increasing, but for the 6 days it start to decrease, and then 6 and 7 days it decrease. So finally, we decided to use the energy of past 5 days in the same hour. For the features, we also tried the same thing. We use from 1 day until 7 days. We tried all of them. We find, it first increase until the 6th day it starts to decrease. So we use the feature of past 6 days.
Okay, thank you.
Thank you very much, Lishon. In feature set 1, you're combining based on timestamp and base station ID alone. So I want to ask how did you select these two, and how did you leave out some things like antenna ID or RU type or some other parameters? How do you select only timestamp and base station ID to combine, please?
Okay, so for this issue, what we did is we tried it because for other like you said RU type and mode, it is not exactly like float or integer. Instead, it contains some it is like some string. So we try to the first thing we try is we give the number like RU type 1, we mark it as 1. RU type 2, we mark it as 2. Finally, it didn't increase too much. It didn't increase, actually, it make our score lower. So we try other method, that is 1 hot. Finally, it show the 1 hot also doesn't increase too much. So we didn't use it. As for your question, how do we select these features? What we did is experiment. We try it and see whether score increase or not.
Thank you.
Okay, thank you so much. I would like to go to the next presentation in the interest of time. So the next one to present is going to be Rajat and Krishna. So the floor is yours. Please, you have 12 minutes, 8 minutes for your slides. So make sure that you are on time.
Sure. Okay. Rajat, I think there's something on your screen which is blocking the slide. Can you remove those?
Is it fine now?
Uh, no, I don't think so. There's still something on the top and at the bottom.
Okay, that must be the one. But yeah, please continue. I think
Okay.
that should be.
Cool. So thank you for this opportunity, Thomas and Nicola. So as mentioned in the first presentation, this competition was mostly about predicting different energy consumptions for different base stations for different locations. So we move to the next slide, Rajat. Yes, so mostly our presentation will be a combination of problem understanding, data understanding, what are the processing steps that we took, and finally, what kind of model did we select and why did we select those models, and finally, what do we learn from this particular competition. So as Nicola explained in his slides about the problem and the objectives, this is the same repetition of the basic problem understanding and the objectives. So we can skip this slide also. Right. So now we'll directly go into the observations that we had from the data itself. So the raw features that were provided to us for each base station was load, timestamp, different power saving modes, RU type, mode, and frequency, bandwidth, antenna, and TX power. Now you see that there were 6 power saving modes, but we did not utilize 4 ES power mode 4 and ES power 6. The reason was very simple. When you group by a particular base station, there should be a variation in the features that we use. And ES power 4 and ES power 6 did not have any variation. Basically, the standard deviation was 0 when we group by at a base station level. And that is why we did not use those features. And essentially, even though if we tried using those features, there was no contribution of those features in the model. Now coming to the first graph. The first graph that you see is with respect to time, how is the load changing? And the second graph is with respect to time, how is the energy changing? What you see here is that load and energy both are very much hour of the day time dependent. There's a very high seasonality between the day of an hour of a day and the energy consumption. And this led to some conclusions that you'll see in the modeling section. The second graph is the variation of energy, and we see that energy has a skewed pattern, which is a real world scenario. Right. So third graph basically shows you a scatter plot between load and energy. Here we also see that there's a linear pattern between load and energy, which also tells us that along with the hour of the day, the load is also a very important factor to predicting energy. Right. Now, since I told you that there is a very high seasonality with respect to hour of the day, we wanted to create some features out of the hour. So although we had an ordinal column of the hour, but we made a spline transformation out of the hour column. This particular feature basically helps the model understand the discontinuity between the 23rd hour, which is the midnight, and the 0th hour. Right. And along with this feature also tells the model that during the morning hours, the energy starts increasing, and during the night hours, the energy starts decreasing. So along with this, we also know that there could be a target leakage in the problem. That is why we had passed 3 values of each features to provide the model an idea about the temporal behavior with respect to energy and other parameters of a particular base station. And this number 3 was selected based on the PCF plots that we had made for the base stations. Right. Now, along with the other features, what we also saw that there was a correlation between load and energy, but there was a huge amount of noise in the load, and this led to overfitting in the predictions while predicting for energy. And that is why smoothing of values of load feature was very important. For smoothing, we use 2 different signal processing techniques, which is first one is Savgol filter and the other one is SOS filter. Both of these techniques, so for example, Savgol filter takes in the past 5 data points and it fits a cubic curve on the base of past 5 data points, and it smoothens the present data point on the basis of this. So this smoothing feature also led to a huge improvement and reducing the noise of the load feature based on which energy was being predicted.
So yeah, for the data pre-processing part, I think as described by Krishna, so we started with the pre-processing steps. So we started with the data cleaning part. So in terms of how we decided that which features as per the ES mode that he has described. Then we started with the ordinal encoding for base station specific information like RU type and mode. Then for the cell name information and other attributes, we also did the same. Other than that, we also created static date time features. Now, according to the feature engineering, that I think some of the points that Krishna has, already mentioned. So we started with the data transformation for timestamp features, the static ones. Other than that, we also went ahead, for the periodic spline transformation of power. We also created some of the feature bins, for load. Also, in terms of those, we also created lag features for load ES modes and other base station specific variables such as bandwidth. And the last but not the least, in terms of smoothing our whole data. So basically, we went ahead with some of the signal processing attributes for the Sapgol filter as well as the Butterworth filtering time things. Now, the main part for our modeling process started with the cross validation part. So, we basically we understand, okay, so basically there are three main objectives of the problem statement. And according to that, we basically devised that group gray fold, okay, in terms of dividing base station to a certain fold and then predicting on some other base stations, irrespective of the base station, because in our particular feature set, we have basically dropped the base station features such that it doesn't create any kind of, such that it basically helps in generalizing that particular stuff. So, and accordingly, this is one more, I think, point. So I think with all of these features, I think basically to address the target leakage, we basically took a strategic approach. We didn't also involve any kind of aggregated features because they could include some of the temporal inputs to that. So I think we meticulously engineered time-based features that basically exclude any use of the future data. Now coming to the model building part.
Yeah. So we started with bagging models, boosting models, but very quickly we figured out that
1 minute to go.
boosting models were overfitting on this data. So after certain iterations, we figured out that ANN models, and specifically 5-layer ANNs after various iteration, first layer being 256, 512, 1024, 512, 256. This particular combination of layers, with each layer being a dense layer. Along with this, so we had 51 dense features, and 3 of the ordinal categorical features, which were load, RU type, and load bin. These were passed as an embedding layer, each having 16 neurons. So 16 multiplied by 3 plus 51. These were the set of input neurons, and these 5 layers were the hidden layers, and then we predicted the energy. So the Keras ANN model, which we developed, has the best score on the local as well as the private leaderboard, which is 0.0435. That is all.
Yep. So I think now coming to the model explainability, I'll not maybe, in the interest of time, I'll not go in deep, but basically for the model explainability, we divided our, base station in 2 separate ones. Like one basically we used for existing base stations and one for the new base stations. And there are few great, insights basically we derived from this, such that, so basically one kind of model would be very much sufficient to basically predicting both kind of these particular base stations, whether existing or new. Other than that, there are some applications of future work which we also targeted in terms of resource allocation, like using some new features according to location and some dynamic configuration, as well as some machine learning advancements as well in terms of using some different activation functions as well. So yeah, I think that's all for us.
Thank you so much. I would like to ask Nicola and Vishnu for some questions, but also there is a question in the chat, so you can also take that. How we achieve accuracy prediction across different base stations.
Right. So if we talk about the final model, which was the 4% MAPE model, so for the existing base stations, when we divide the data, we had around 3% MAPE for the ones for which that past history was present. And for the newer base stations, we were able to get around 6% MAPE. And together for the whole data, we had around 4% MAPE. So we can go with the questions. Yeah.
The floor is yours.
I would like also to ask a question. Can you hear me, first of all, because I have a bad connection?
Sure,
Yes.
we can.
Yes.
Okay. So I see that you have done a lot of analysis on the explainability and also on the feature engineering. I would like to ask you which was the most challenging part in this competition. So while trying to solve the problem, which part did you find more challenging?
Right. So there was one nuance in the interest of time which we could not discuss in the modeling part. So see, mostly what we observed in the first few days is that the data provided was very much overfitting any kind of model that we were using. So we after first few iterations we skipped the boosting models, but when we started with the even with the ANN based models, what we figured out is that we started experimenting with different layers and everything. So if all the iterations were giving us incrementally better results, but one major experimentation was the activation function that we use in the ANN model. So generally we go with ReLU functions, right? So but in this particular competition already we had made features which would tackle overfitting, but we also experimented with SILU activation function in the best model. Now one major difference between SILU activation function and ReLU activation function is that SILU is basically x multiplied by sigmoid x. Now what happens is that due to this particular function, ReLU is a monotonically increasing function, but SILU is not exactly a monotonically increasing function. And so what happens is that it does not, for the larger inputs, it does not explode the weight for those inputs. So what happens is a particular neuron's weight is not much more with respect to any or the other neurons. So what happens essentially using SELU is that all the features are given almost equal importance instead of model just relying on load or any smoothened version of load. So to answer your question in short, controlling overfitting was the most important factor.
Thank you.
Okay, there are two questions in the chat. Using energy T-1 and energy T-2 may introduce future values. Can you explain how it does not? As well as on smoothing may also use future data if window is not properly picked. So can you try to convince us on that one?
Right. So I'll take the easier question, T-1 and T-2. So as the name suggests, it is not T+1 and T+2, it is T-1 and T-2. So basically we're using the past three value and past three values. So there are two kinds of features. One set of features are the features which capture the physical properties, the instantaneous values, right? And the second type of feature is the past temporal data. And we wanted to make a single model which captures both of these things. So in our iterations, we also made two different models. We had this idea that we could make two different models, one predicting for the base stations where we have history, one predicting for the base station where we do not have history. But essentially that would lead to more complexity, and if we can introduce a pipeline with a generalizable model, that could be a very unique proposition. So that is for the first question. The second question of smoothing features using future data. So we knew that this could be a problem, especially for the aggregate data. That is why we did not use it. So to give you an exact detail, both the filters, for example, I mentioned for Savgol filter. Savgol filter has two different inputs. One is the window length, and the second is the polynomial order. So window length, so for in our case, window length was 5 and polynomial order was 3. What this basically means is for a particular load value at a timestamp, when we want to smooth that particular value, what it will do is this particular point and the past 4 points, it will use five of these points. And since we know that the curve is it is not a quadratic curve, it is a cubic curve, the variation in the energy. That is why the polynomial order was 3. So on these 5 data points, it will fit a polynomial order of 3. And then the last data point, which is our current data point, it will smoothen the value of that particular data point. So even when you have this model in the production, always the last data point of the test data will be smoothened out.
Oh, sorry, I asked this question because you may be wrong about that part. In your case, if you have 5 observations, you are using the Windows 5, but actually it's using the 2 of before and the 2 after. So you are using the future data. You are actually filling the middle one if you use the default parameters. You can check that parameters. Yeah.
Yes, so that is generally the definition of a window, but not in case of Savgol filter and SOS filter. So that is
No,
what
no, I think the way is like he's using filling the middle one actually, the default one. But of course, you can shift to the window. But if you use the default settings, you are kind of introduce the future data. But I could be wrong, but that you should double check that part.
No, so you're right. So when we were implementing this, and even after implementation, we went into the source code of both these signal processing functions because they're already used in different production environments. These two functions of forecasting
Yeah.
problem.
So you're
So
saying you just implement yourself, but yeah, you are right, maybe you're. But if you use the default package from statistic, the default one is like what I said, is kind of using future data. But it just we can take care of that part. Yeah, thank you.
right.
And also
Okay.
one more thing, basically we are not using this particular filtering mechanism for energy. We are just using this for load.
Load. Yeah. So this is not smoothing of the target variable.
But for that part, I still see the load, even load is still future
Okay, so
data,
let's
right?
take it in the chat. So let's continue with the presentations. We still have a long way to go. So thank you so much. I would like to go to the next. Raphael, you are the next one to make the presentation.
Hi guys, my name is Rafael. I am a competitor from Brazil, and the first thing I want to say is my English is not perfect, and I will try to express myself better I can in 8 minutes for this presentation, okay? This is my presentation. I think here. Oh, sorry. Okay, this is my presentation. My model, do you see my presentation? Everybody sees my presentation? Yes. Okay. My model is a hybrid Booston model with approach inspired by mixes of experts. And in this presentation, I will talk about preprocessing, assembling model, approach about mixture of experts, and the model workflow. From data merging and aggregation, we combine the training and test set, doing the merge left in cell level in base station, and doing aggregation in the cell columns using sum in load features. And in special cases, we do the mean, like this in frequency. Cell name is sum. You do the sum in cell and cell 0 and cell 1. This is why we need this aggregation, okay? The feature engineering standard features is not temporal features. We do date time, label encoding to categorical columns, discretization from some continuous features, and one hot encoding just to area type. Okay, just that. So this is the part I think everyone wants to see. And this is the temporal features. You use common lags for energy, load, hour, day, MS mode 1 and MS mode 6, sorry. And target encoding, especially just for hour. What this means? This means target encoding is treated like a temporal feature. So just every aggregation I use for this problem is treated like a temporal feature because I will explain. But I do difference to the lags, and every feature is temporal feature is generated by grouping the base stations and safeguard temporal integrity. What this means, they use this Boolean variable, and if I want to do data leakage, I use all I see all the data, for example, to do target encoding. If I don't want to do data leakage or future leakage, I use a cumulative target encoding model. What I do, I sort the time sorting. I do the cum sum and the cum count, and then I populate this aggregation can be target encoding, can be anyone, just with the past data. The data is sorted, and I do the population just in past data, okay? That's in this competition, this is important. You can do data leakage, direct visualization to filter data using lead or using befilling new values, for example. The only way to not do this is avoid direct visualization methods. And you can do future data leakage aggregating with methods that include future data, like target encoding, min, max, every aggregation that sees all the data that's one time, because when you do this, you look to future data because the index is a time, okay? So here is my final submission, 0069. With I add the global aggregation, I have a best score because it's 0069. I have an improvement to see all the data. And if I use leads and the global aggregation, I have the score 0050. So if I use future data, we have advantage to other competitors. That's what I want to say. That's just my opinion, okay? So assembling model, it's my model. It's a ridge regression with XGBoost on the residuals. So we predict the ridge and then use the residuals to with XGBoost, and the final we sum the ridge and the XGBoost, okay? So the approach inspired by a mix of experts. This approach allowing me to develop 3 specialized models for a specific object. So object 1 is the expert 1, object B is the expert B, and object C is the expert C. This is what I do, okay? So object A capture historical seasonality. This is the best way he provides the best scores, who uses the historical seasonality of the base stations, okay? Expert B, it's a hybrid method. He uses historical of the base stations, but he always uses advanced feature engineers to the object to generalize over new stations or higher stations. So I use polynomial features, k-mean clusterings, and the objective here is reduce dependency on historical data and emphasis station settings and load settings, okay? And expert C is a simple model. We just use the features we have in the data, and the primary objective is do not lead to overfitting or do historical contamination, okay? So the gate is a part of the mix of experts, and the gate is our system to segment test data into hot and cold. So you use BS and RU type to segment the data to appropriate expert for its situation, optimizing precision and adaptability. So the object A, we have in the test the BS and the train the same BS, the RU type in the test and the train set. And we have this mask W1. For ask W2, we have the BS. We don't have the BS in the test set, but we have the configurations of the base using the RU type. So we have another a hybrid generalizations problem. And W10, we don't have the base and don't have the configuration. And this is the most difficult problem because it leads to much more generalization problem. So this is the model workflow as representative by this scheme. We have the data cleaning and then the future engineer. we have the
30
expert
seconds to finish.
Okay, I will finish just in 1 minute. I have the expert A, expert B, and expert C. They have the all processing and training separate pre-processing, expert B and C using subsampling, and then we go to the gate and to the final predict. Why I think this is a good solution for this competition? Because you can see clarity for the third objectives. You can see what expert A is doing well. You can see what expert B go well and what expert C go well, and you can see this in the objects too. So this is my approach.
Okay, thanks. I'd like to ask Nicola and then Vishnu for Q&A.
Okay, let me go. Hi, Raphael. Thank you for the presentation. It was interesting about this multi-expert approach. I would like to know more about the complexity of this approach. So how much time do you need for training? And if you can elaborate a bit on the complexity of your solution.
Yes, the complexity is one of the problems of the solution because we have 3 experts instead of just 1. But this, as I say, I can separate the problems in the way I can see what doing well for each object. So I do a modification and I see in this expert C going well. Oh, I do this modification. Oh, expert B going well doing this. So the this is more complex, but it's a form to see the problem. You can just input wherever you do in one just expert and try to see what's going on. In this model, you can see what's going on. So for me, the complexity is not too great because this is an advantage I can use. Okay.
I see. Could you provide some number on how much time you need to train? So in minutes, which is the order of magnitude, just to understand.
I don't get it. Sorry.
So how much time do you need for training your model?
Okay. It's 2 minutes for each fold. I use 10 folds with multi-stratification. For each model, I have different columns for stratification.
Okay, clear. Please, Vishnu.
Yeah, very interesting. Yeah, thanks. And yeah, good discussion. The time factor, Raphael, why you did not consider the time factor at all?
The column time yeah, I think because I see in the problem the hour is the most important feature for me. For example, if you see the time, because we extract the time in our day, and the day is not go so well, but the hour, as you look the hour in the 7 days, you see the seasonality of each base station, and this for me is the most important time feature. Of course, you have to lead with the data leakage of future data, and the first days we don't have so much data, but when you resolve this problem in real, I think you have much more historical data. So this problem, you don't have this problem to the first 1, 2, 3 days. You don't have data sufficient to see the real seasonality or the real user traffic of this region of that base station.
Okay. Thank you very much. Thank you.
Okay, thank you so much. I would like to go to the next presentation by Julius. So Julius, the floor is yours. You have 12 minutes, 8 minutes for presentation and 4 minutes Q&A. Please take it out.
Thank you. Thank you very much. I trust that you can see my screen.
Yes.
All right, great. So that's me, Julius Maina. So agenda is to do an introduction, then to do my proposed solution, and also discuss the results, and then conclude. So introduction, I think this has been already been mentioned by Nicola. So I may not spend a lot of time here, but the 5G revolution is that the 5th generation of digital technology is driving a profound transformation in connectivity. It promises faster speeds, lower latency, and new other applications. So, but there's a challenge, and this challenge is the energy consumption. So, you know that the complexity of 5G networks, they are resulting in a substantial increase in energy usage. So, Nicola explained very well that the majority of operation costs, they are around 25% from energy bills, and more than this, more than 70% of this energy is consumed by base stations within the radio access network. So optimization is key to mitigate this substantial energy footprint. Optimizing base station parameters and energy saving method is paramount. So accurate modeling of energy consumption is quite crucial for achieving energy efficient network deployments. So my approach, I strongly agreed with the host that this was not a time series problem. Therefore, no time series approaches were pursued. Instead of the normal k-fold splitting, I did a repeat k-fold, which seemed to work better. And then I just used one model, like GBM, after comparing its performance with other models that I'll be discussing later. So advantages of this approach is that there's no need to track lag features because it's not a time series. There's no moving averages and such kind of features. It also reduces the complexity, which is now easier to understand, even implement. So faster training and inference is also another benefit. Okay, move to the next. So I did quite some data cleaning, which my method benefited from this a lot. So the data cleaning, first I removed the energy saving mode column, which had just constant zero values. So they did not add any variability in the data set. So that column was dropped. I also tried to harmonize to ensure uniform antenna counts across the base stations. So what I realized is that one of the data sets, the base stations, and also the cell level data set, you could see some inconsistencies in the number of antennas for the same base station. So I had to harmonize these by just doing some count, by just doing some voting kind of counting to ensure that I don't have variable antennas for the same base station. So I also label encoded the categorical features or the text features so that they can be used by the model. So there was also optimizing the data for analysis by restructuring using pivoting with the cell name used for restructuring the data set. From there, I went ahead and engineered some features. Initial meta features, I used 14, the one that were given from the data sets, except time and ES mode. Of course, I didn't use time, but definitely I used time to come up or hand engineer the temporal features. Among them was the hour, the day of the week, whether another feature to test whether the day is weekend or not. Another set of features that I did that really boosted my scores was just trying to know what power saving modes were active at any particular hour. So I would combine maybe ES mode 1 and ES mode 2 to see whether both of them were active at the same hour or only one or maybe none. So those that set of features really helped my models in generalizing very well. So I also did some dummy features for the radio unit type and also the mode of transmission for this radio unit. So I also did some domain relevant features, e.g. comparing the bandwidth per every antenna, load to TX power ratios, bandwidth load and workload to antennas, and some other X power load interaction features. So after that, I ended up with 106 features in total. And then I trained my light GBM regressor, which is efficient for handling missing values. I did not fill the missing values. I also did not drop the missing values from the data set. So I had to resort to models that can really use missing values, that can work with missing values. And one of them is the light GBM, which also ended up to be my final model for submission. So performance, I was just training on a CPU on a 16 GB RAM size computer. And then I tracked the accuracy, which measures the overall correctness, calculated as the ratio of correctly classified items to the total number of items in the data set. I also, of course, we tracked the weighted mean absolute error, mean percentage error with MAPE, that is based on the competition platform calculation. I also tracked the training time and also the inference time. So for the model of choice, this is the light GBM, and even the other three. I also tried cut boost, XG boost, and history gradient boosting. All of them using this set of parameters, the objective squared error for regression tasks, and then also utilizing all available CPU cores, that is the N jobs, the depth of 3, the learning rate of 0.1, and boosting rounds of 10,000 for model training. So the rounds were quite many. So performance.
30 seconds to finish. 30 seconds to finish, please.
Thank you, Thomas. I'll be fast. So performance, I realized that light GBM using K-fold performed the best in all the metrics compared to the rest. Oh, I have an incomplete table here, which is not yet done. Some errors there, but light GBM became the choice model after comparing it with the rest. So performance, and then for this light GBM, I tried to compare the K-fold and the traditional K-fold and tried repeated K-fold, and I realized that the repeated K-fold was generalizing better compared to the traditional K-fold. So that's how I settled with the light GBM. We generalized better than all the three algorithms, and did a repeat K-fold, which generalized better than the traditional K-fold. And you can see on the right that the load, base station features, and domain-dependent features, and even the hour features were among the most important features in my model. So future work, more hyperparameters can be added to my model. I can do some tuning, maybe using Optune or grid search. I can enhance more features and maybe try deep learning and artificial neural network, or maybe even a simple model. So that is it. I think I stopped there in the interest of time. Thank you.
Okay, thank you so much. Thank you so much. I would like to invite Nicola and Vishnu for Q&A.
Hi, Julius. Thank you for your presentation. I have so I've seen that you did some end engineering of the features. So you have many input features with respect to what is in the dataset. And I'm curious if you can elaborate a bit more on the gain that you achieved thanks to this approach. So how much was the accuracy improved when using end-made and engineer the features with respect to the case in which you just used the original features.
Okay, thank you so much. Initially, when I used the original features, I realized that my scores were quite low. To be specific, my mean absolute error, because at that time the private leaderboard had not been revealed. But after the revelation, I realized that my WMAP was around 0.20, 0.2. 0.2 is quite high because after adding these other features, we can see that my KFOD finally has a private score of 0.09 with the additional features compared to the original, which had 0.20. So the deviation is quite big. The models could not generalize well with the original features.
Thank you.
Okay.
So Vishnu,
You're on mute.
yeah.
Sorry. Yeah, I think the hand engineered features are quite interesting. I had the same question as Nicola. I think the domain-wise engineering, feature engineering that you have done, that is quite interesting. That is quite relevant as well. However, I believe that it's not clear to me how you have combined, if at all, is there any combination of the base station values that you have done at all, or not at all? I'm not able to. I don't get it from the slides. So I want to ask if there is any combination of base station specific values that you have done, please.
I'm not sure whether I understand. You mean combination of base stations? Which base stations?
Right. So let's say the TX power, transmit power, or something which is based per base station on an antenna basis, right? That's what is given in the data set. So when do you combine at all or not on a time basis or any other basis?
No. There's no combination. So I just take the features for every row, and then I then hand engineer the features for each row. There's no grouping. There's no combinations.
Understood. Okay. Thank you.
Thank you.
Okay, thank you so much. Right now, I'd like to go to the next speaker, Isaac, who is going to make his presentation. So, Isaac, you have 12 minutes, 8 minutes for presentation and 4 minutes for Q&A.
Okay, thank you. Okay, thank you. Good afternoon, everyone. My name is Isaac Brano. I'm from Ethiopia, and I will present my proposed solution for 5G energy consumption challenge. Okay, so 5G networks has a good significant advantage over 4G and 3G network technology, but it costs more energy than 4G and 5G networks. So this 5G networks has impact on climate and environmental factors. So this energy consumption of 5G must be optimized and used efficiently. So machine learning methods to optimize the usage of consumption of 5G network consumption. So we can identify which base station used more than expected energy And we can evaluate different energy saving methods, and we can also use in energy efficiently in different products. Okay, to train my models, the data had 3 data frames. One was cell level and the base stations and the energy data frames. So what I first pivoting the data frames, because some base station has more than one cells, so I pivot them. That means just pivoting the load, for example, load in 4 cells, and pivoting like boundaries and another columns like this. Then the merging with the original train and test data frames. Okay, let's go feature engineering. I use the different feature engineering methods to overcome this challenge. And the first feature engineering methods was adding and counting features. Okay, this is how to work. First thing is summing the base station feature in row wise. That means we pivoted the loads and the boundaries. So what we do, just summing that different columns, for example, different load columns in each row. So, and then summing another like boundaries or TX powers. So summing was the first one, and counting unique value. That means in each rows, if there is different antenna used in base station, just counting that the difference if used the different antennas or boundaries in each house. And another is clustering features to get the similarity. And I used the PSA to decrease the features dimension. And also I did a grouping by base station, taking the max value. This gives some information about the behavior of base stations. Another feature engineering method was moving statics in lag features. I compute the difference of loads and energy. And also I compute the ratio between consecutive value. Then I took the rolling mean and the standard deviation and max mean. And I used load. I shift forward one t plus 1 load columns. Then I take the lag value. That means I shift in t plus 1 and take the lag of 12 hours, 24 hours, and 36 hours. And also I use the Prophet model to predict the load in next hour. That means there was high correlation between load T plus and the energy consumption. So what I did, I used Prophet model to predict the load columns. Another feature engineering was inside of BSA. What I did by grouping the in base stations, then I take a cosine. I take compute the cosine similarity between load and the energy times energy, and taking the fitting in linear regression model and taking the coefficient of load, hour, and count features. Then just giving for that base stations, and I take mean absolute error when we predict the in linear regressions. What's the mean absolute error in that base stations? And another was a correlation coefficient. When we do these things, I found some interesting thing. Some base station had negative correlation with energy. So I take the correlations, then give for all base stations like this. And I also did fit in random forest regressor and predicting the energy, then taking that as a input value. Okay, another feature engineering was target and the meaning coding. This kind of feature engineering had high feature importance. First thing I did taking the base station and the base station without just I use the cut the target encoder, then combining them, and another is in load.
1 minute to finish, please be fast.
Okay. Another is in load features. I use the meaning coding on load features. I use the T plus load, then just I compute the mean of in each hours. Another feature engineering was probability increasing. This kind of feature engineering gives more importance. How this work? If the load and the energy take the difference of load and the energy, then what I did, if the load and the energy increase at the same times, then just then that with the probability of increasing each hours. So this kind of featuring has good importance. And another was hot encoding and a load value. First, I just take the quantiles, then computing one hot encoding on that quantiles. Okay, my model result was this 0.075, and this is top feature importance, and the difference of energy in base station in each hours has had a more feature importance. And in future times, this data has some structurality and there is some seasonality. So LSTM energy may be well performed in this data, and using analyze and using more feature engineering help to improve this problem. And thank you.
Okay, thank you so much. Right now we go to Q&A. So Nicola and Vishnu, the floor is yours.
Okay, thank you for Isaac for your presentation. I saw a lot of feature engineering. I'm not sure I got well which machine learning model you used. So if it was a gradient boosting or something else to estimate the energy consumption. Could you please explain me better?
What?
So which model did you use to estimate the power consumption? So was it, I saw LSTM at the end, but I'm not sure which one did you use.
Okay, I didn't use deep learning methods. I used the light GBM models.
Okay, light GBM model. Okay, great. So the question is, did you try also others before selecting gradient boosting? Which was the process that made you choose gradient boosting as a model?
Okay, the light GBM model, the data has a lot of rows. So for my experiment, I like to experiment more, and I went to train and see my result in less minutes. So light GBM model has a fast than others model. So for that.
Okay, so it was based on the complexity. Let's say it's more faster to train than others. Okay, so Vishnu, please, I'll leave the floor to you.
Thank you very much. Yes, I believe the clustering, the data engineering, feature engineering which you have done is quite important. But I don't know whether how you went about it. How did you select this clustering without RU and the probability based on increase and load and cluster? How did you select that engineering? How did you select this? Because this is determining, basically in your case, this is determining the final score. That's why I'm asking.
What, please?
How did you determine the feature engineering? How did you How did you select the feature engineering technique parameters, please?
Okay, I think your question is in a clustering and a cluster without RU. So and dataset has a RU type 12 and 11 had only one row. So almost that means there is no that the model cannot take the behavior of that RU type 11 and 12. So I treat this RU type and RU type 11 and 12 as a unseen data. So when we take only RU with RU, just when we predict any all columns on all RU type 11 and 12 cannot take that the weight because it also missed in that in training data. So I need to feature engineering with RU type without RU type to balance all for all predictions.
Thank you.
Okay, one last question. In your prediction, right, you are adding a constant 15. Why are you adding that?
Okay, so when I see the data frames, so RE type 12 had more than 32 antennas. Most of antennas in training data had less than 32. Most of 75% is less than 60. So the antenna had a high impact on energy consumptions. So when we train on a less than 32 antenna, and then when we try to predict in a RE type 12, that means that are more than 32 antennas. So cannot predict good enough on the more than 32 antennas. So I think that for that.
Okay. Now I go to the next presentation. So the next one is Tingwei for the presentation. So can you start sharing your screen? Yes.
Okay, I will share my screen. Okay, everybody see my screen? Hello?
Yes, you can start presentation.
Okay. I'm Ting Wei, and on behalf of our team, Kate, I'm here to show our solutions. And our team members include Ting Wei Chen, Yan Tao Wang, Han Zhichen, and Zhijian Zhao, Xinhao Li. And we are from Shenzhen Research Institute of Big Data. Let's skip the background since for saving time. Our system model is as follows. After the data processing, the hybrid feature selection module would produce two feature sets. Then they are evaluated to generate the energy consumption for sets with and without BS information. So moving to the data preprocessing stage, we by analyzing the raw data set, we can understand which parameters we can utilize and how to process the data. Initially, we found that for given BS, the IU type and the mode remain consistent. And a BS can serve multiple cells at the same time. So therefore, we merge the BS info and the cell level data, resulting in the data structure shown as this table, as the first table. And however, in most cases, some a PS only serve one cell, so other cell loads are generally zero. To further simplify the data, there are some categorical features that we cannot use directly, such as the IU type and mode. So we applied one-hot encoding. Also, from the repeated experiments, we also found that some certain numerical features, they don't represent size or sequence, and they are also one-hot encoded, such as the antennas, bandwidth, and frequency. Below, we listed our data format, look like the second table. This is our basic data processing. So, and on the next page, we move to the feature selection stage. During our data analysis, we discover some values in the training set that remain consistent. They don't help in the neural network training. So, and should be removed. Also, the features with only one unique value in the training set can lead to overfitting. So we calculate the standard deviation if they are lower than 0.01. They should also be eliminated. And next, I will show our network and the modules we have utilized. Since the BS feature in the test set does not overlap with the training set, so using this information, but we found using the BS information can enhance the prediction performance. So as evident from our submitted results. Yeah. So on the left is a naive, deep feed-forward network comprised of linear layer and batch normalization layer and activation layers. It is very simple but it performs well when BS is used as an input. However, when BS isn't an input, the model on the right, which includes excitation, which is an attention mechanism model, gets better results. This is because it focuses attention on more critical features, giving them more weight. So our best performance comes from combining the two networks. When the input BS exists in the training set, we use the naive DFN. When it doesn't, we use the DFN with excitation. So the next page covers some our experiments. Since we don't have the ground truth for the test set, the following training loss trends across epochs, along with our submitted scores, confirm that the one-hot encoding certain numerical features and using BS as an input can enhance the performance. So that's all. And our solution employs a hybrid feature selection method combined with an attention mechanism and enhancing both accuracy and generalization capacity. So, and here is our best scores in the recent submissions. Yeah, thank you.
Hey, thank you so much. Now we are going to Q&A. So Vishnu and Nicola, the floor is yours.
Thank you, Tingwei. Very nice presentation. I would like to ask you about the deep feed-forward network, and in particular, what is the dimension of the feed-forward network and how you selected that dimension?
So our dimension is determined by
Number of
our
layers.
original.
Yeah. For example, number of layers. Yeah.
Can you speak again?
I would like to know the dimension, in particular, the number of layers of the deep.
Okay.
Yes.
So we just use 7 layers. So the input dimension is 1160, and the second layer is 1024, and next is 512, and next is 200, so on. So we the last layer is. Yes.
Have you tried with the smaller network to see if it? I mean, if the accuracy is worse? How did you select this dimension?
We just do repeated experiments and find the best is start from the 1024.
Okay. And have you checked or investigated the trade-off between the accuracy and the complexity while changing the dimension of the feed-forward network?
Yeah. Actually, we have low complexity since we train a model less than 20 minutes. It's very simple and effective.
Yes. Thank you. Please, Vishnu.
Thank you very much. The merge base station information and cell level data, merging of base station information and cell level data. In that, what exactly are the parameters which are merged? Do you merge the bandwidth and frequency information also? Or not, please?
Yeah, we use all of the features we can use from your raw data set, and we just do the one hot encoding for the features as below here, and other actually we will also do a combination with the cell name, since there are 4 cell in the data set. So every feature is combined with cell name, like the second table here. You can see the ES mode 1 cell 0, ES mode 1 cell just like this. But the mode and the IU type, they are determined when base station is given. Yeah.
Okay, thank you. Yeah.
So
thank you so much. Okay. I would like to go to the next presenter. So the next one is Alexander. Yeah, please share your screen and start the presentation. You have 8 minutes for presentation and 4 minutes Q&A.
All right. Can you confirm seeing my screen?
Yes.
Still?
Yes, you can start.
The prediction of energy consumption is a vital element in the process of expanding the 5G network. We are students from Poland. My name is Chris, and I will present the Montex machine learning model and the process that led us to developing it. First step was data mining. Standard approach in processing sequential data is utilizing UMAP for data visualization. This revealed distinctive patterns. The stripes on the chart highlight the recurrent dependencies in the data. Histograms showed the data distribution was most uniform on an hourly basis. Please see the diagram. The consistent hourly distribution was observed in both training and prediction datasets. The neural network structure does not consider data from cells 2 and 3. This decision was made due to barely 48 instances where cells 2 or 3 appeared in our dataset. Consequently, it was deemed efficient to exclude these instances from our model to simplify processing. There was a notable imbalance in the amount of data for single-cell base stations compared to multi-cell ones. To address this, separate neural networks were implemented for different base stations with different number of cell data. This ensured efficient processing, particularly since a significant number of stations were single-cell, eliminating the need for extensive zero padding. Data pre-processing, padding. When constructing the time series input, certain data points were missing from both training and validation sets. Instead of leaving gaps, the last known value was duplicated to represent the missing data points. For optimal processing, as mentioned earlier, padding was done on an hourly basis, yielding the best results. This process is being done only for data where cell 1 is different to other cells. This approach ensured a continuous flow of data for more effective model training. As visible in the diagram, the input was a vector consisting of data from last 3 available timestamps. As previously indicated, no cell 2 and 3 data has been used. We also used one-hot encoding for the RU type attributes to get rid of similarities between adjacent RU types. Energy 1, so energy from the previous hour, turned out to be a very important attribute. The final model. In the diagram, you can see gated recurrent unit. We evaluated the performance of several neural networks, models such as recurrent neural network, XGBoost, and GRU. The RNN XGBoost model lagged in performance with GRU model outperforming it. Recognizing the strengths of static neural networks in managing gaps in time series data, we used them to fill gaps in the training set. This was done without using future timestamps data to maintain the integrity of the competition's rules. The fully processed training data, enhanced with the MLP model, was utilized to fine-tune our GRU model for optimum results. The used static model was a 3-layer perceptron with 512 and 128 neurons in hidden layers, with batch normalization after each layer, and the relay activation function. This output was used to train a GRU model. Expanding the training dataset by approximately 20% through the addition of data generated as predictions by the static model allowed the final GRU model trained on such data to achieve improved generalization capabilities. The used recurrent model was a GRU network with the 2 recurrent layers and 512 neurons with batch normalization and ReLU activation. This concludes the presentation. Thank you for your attention, and we are happy to answer your questions.
Yeah, thank you for the quick, brief presentation. I would like to give the floor to Nicola and Vishnu.
So thank you, Alexander, for your presentation. My question is similar to the one I asked before to another participant. In your case, you have decided to input the 3 previous time steps, so the 3 previous hours. I would like to understand how you selected these numbers, so why the previous 3, if you have tried using more or less historical data, and to see how these impact the accuracy that you achieve through your model.
So I guess we did that kind of empirically. I guess there are a lot of issues with padding the missing values, and well, a shorter window, let's say, provides more, I would say, accurate representation of reality. I guess, yeah, like I said, mostly an empiric decision. There wasn't much change when we implemented, let's say, larger input vectors. I guess, well, this finally performed the best, but there was no clear trend to the performance.
Okay, and have you analyzed how having how providing this additional information affects the performance of your model in terms of complexity? So is the complexity increasing a lot, or how much, with respect to the fact that you are providing more inputs?
By complexity, do you mean like the number of parameters?
Like a running time to train the model.
I mean, the running time wasn't an issue, to be honest. I would say at all instances, the, let's say, training time was, I don't know, in a minute or two for all the models. So no, that wasn't an issue. Yeah.
Okay, thank you.
Thank you.
Yeah, thank you very much. What is the, you says that there were separate neural networks were implemented. Can you tell what are the, due to that, how your final scores changed? Did you take different approaches, or how this affected your final scores, please?
Okay, so due to let's say having different amount of cells in particular base stations, we decided that it would be best to implement a neural network for cases that have only one cell and the rest of cases, because we used an hourly padding. We didn't want to use the zero padding, the classical approach with bias disabled in the first layer. So I guess that was kind of forced upon us, but I guess the scores changed. Let's say we had, I believe, with the zero padding networks, we had we barely, I think, got below 0.2 on the private score. Our final score was 0.08. So yeah, that was a large improvement to do an hourly padding over the classical approach.
Thank you very much.
Oh, sorry. Thank you so much for the presentation. Right now, we are going to next presenter, Hamdi. Please share your screen.
Hello, can you hear me?
Yes.
Okay, great. You do see my screen, right? My presentation.
Yeah, you can start.
Okay. So, welcome everyone. Today, I would like to discuss our study on 5G energy consumption. While 5G brings enormous advancements, it also raises energy consumption concerns. Our research dives into leveraging machine learning to predict the energy consumption of 5G base stations. So this is the table of contents. We have an introduction, and then we delve into the parts where we dealt with our data data preprocessing, feature engineering, and model development and validation. And we will finish by results and discussion. So the energy demands of 5G networks are significantly high, especially in the radio access network domain. Base stations in particular account for a substantial portion of this energy. Given the varied nature of 5G deployments, traditional static models fall short. Thus, a flexible modeling approach becomes crucial. So for the data preprocessing, given the complexities of base stations, we refined the dataset structures. For instance, in the base station info data, new columns were introduced to detail the primary sales properties. And to avoid overfitting, we strategically omitted certain sales. A key part of our data processing was managing cell name values. We chose to retain data from the two dominant identifiers and combine other instances into our primary data sets. So for the feature engineering played a pivotal role in enhancing our model. We created new variables such as load sum and load multiplication, which aimed at extracting underlying patterns and connections present in our dataset. To capitalize on the time-related data, we introduced features like hour, sin, and is weekend. Additionally, we compute the power utilization ratio and assessed energy saving intensities, adding depth to our prediction capabilities. Also, we have done aggregated features engineering by clustering our data based on unique base stations identifiers. We dove deeper into the behavior of multiple stations. This approach assists our model in making predictions for unfamiliar stations by learning from known behaviors. To further optimize our model, we converted categorical columns, especially base station, mode, and radio type, using ordinal encoder. Finally, we introduced a function called predict next values. It leverages the XGBoost algorithm to estimate the upcoming load values based on historical data. The process involves storing, iterating over unique base stations, preparing data, and predicting load values. Now, for the model development and validation, let's delve into our methodology for developing and validating the predictive model for energy consumption. Our approach prioritized real-world applicability, starting with the grouping data by the base station, using specialized cross-validation, training with the powerful XGBoost algorithm, and iterative evaluation. Here are the hyperparameters we have used for the XGBoost model. Our choice of regression gamma objective was due to the energy consumption data resembling a gamma distribution. Now for the post-processing, which was vital, especially when our dataset hinted at potential synthesis. Our strategy ensures that predictions uphold that integrity according both known and unknown base stations. Now, moving on to the results of our model. Our model achieved a weighted MAPE of 7.7%, indicating a close proximity of our predictions to the actual values. To further understand this, let's look at the density distribution. As you can see from the density plot, our model's predictions closely resemble the training data distribution, especially around peak values. However, the tail hint at possible areas for improvements. While we are proud of our model achievements, it's essential to recognize its limitation. The data hourly granularity and inherent simplifications in any machine learning model might have influenced our results. Science is a continuous journey to further hone and model. We are considering more granular data and exploring even more advanced modeling techniques in the future. Now, to conclude, our work underscores the potential of machine learning in predicting energy consumption for 5G base stations. We look forward to further refinement and advancements in subsequent iterations. Thank you for your attention. I'm open to your questions.
Thank you so much. I would like to request Nicola and Vishnu for questions.
Hi, Hamdi. Thank you for your presentation. My question is about your feature engineering part, processing. You have mentioned that you have generated some statistical insights in the aggregation phase. Could you provide more details about this?
Okay, so I have grouped the data by base stations and computed the mean of essentially the load of each base stations, which is a critical aspect. Not only the mean, the standard deviation, the mean and max, to give the model an estimation of the range of values that a certain base station might have as load.
Okay, I see. Thank you. And could you also elaborate a bit more on the temporal feature engineering part?
Okay, which one exactly?
Previous. No, I think it's the previous. Okay, this one.
Yes, of course, we have the time column. We extracted some meaningful temporal features like hour, and we did we applied sine and cosine to the hour to give this cyclic pattern to our data. Especially our data have had some peaks around 6 to 10 p.m. and it will reach a minimum at like 4 to 6 a.m. So we gave our model this new features to better extrapolate the temporal patterns in our data.
I see. Okay, thank you.
Okay, thank you.
Thank you, Amdi. The uniqueness, you say only 600 unique values, whereas there are 90,000 records, but 600 unique values. Can you explain a little bit, please? What does that mean?
Yes, after examining our target variable, we found that the target variable had only from 90,000 records had only 600 unique values. So I suspect that the data was synthesized. That's why there is a finite or limited numbers of unique values of the target variable. So I did some post-processing to so that my predictions assimilate the target variable behavior.
Okay, thank you very much. And there is power utilization ratio. What is power utilization ratio?
I believe I did divide the load by the maximum transmit power.
Okay, load by power. Okay. Okay,
Yes.
yeah, thank you. Thank you.
Okay, thank you.
Okay, thank you so much. Right now we are going to, last but not least, Ning, please, you can share your screen and start the presentation.
All right, just a second. Can you see my screen? Yep.
Yes.
Okay, let's get started. So, hello everybody, I'm Ning. I'm also from Canada. So I believe you already know the problem. So I will first talk about the challenge, I think, in this competition. The first one is, I think there are unseen stations and unseen configurations. About 40% of the rows in the test data set actually belong to unseen stations. And not only the stations are unseen, but also the configurations, especially for this type 11 and the type 12. So they totally occupy like 50% of all these unseen stations. But technically, it's not totally unseen because for each type, there is one stations, but for each one, only one data point. I think maybe you are aware of this. And they also have the new configurations, like for type 11, there is a frequency close to 1000 and bandwidth 8, attendance with 64. Similar thing for the type 12. So this is one of the challenge. I believe this is the challenge if they want to solve for the problem C, like Nicola talked about. So next challenge, I think I call it hidden factors depend on individual stations. So I'll give you examples. So two stations, one is 603, another is 728. So you can see they have identical configurations. They're all same. But now let's plot the load and energy. So this is for 603. This is a saving mode. They are zero, so basically it's not enabled. And the blue is the load, cell zero load times 100, because I want to put the same scale as energy. So you can see the blue is like this pattern. And then the energy consumption, energy in the range of 20 to 60 in this range. But for this station, it's same configuration and the pattern. You can see the blue is also same pattern, also it's in the range, but the energy is actually in the 40 to 80 range. So yeah, this is just basically, you can see each station may have a basic consumptions and just belong to that station. So this is not only case. I found this particularly for type 1, because I believe maybe type 1 is sort of an old type, and it may have some configuration or settings that control this basic consumption. But for some reason, this data is not available in this data set. So this is called as a hidden factors. The next challenge we all know is not to use any future data, because if you didn't do aggregation, smoothing, or interpolation properly, you may introduce future data. And I believe this also applies to other columns as well. So yeah, there's challenges. Now talk about my solution. So from algorithm perspective, I choose like GBM as most people. So this is because I believe this algorithm is good for smaller data set, tabular data set like this, and also use a k-fold, 10-fold. So for the pre-processing, the first two steps is just to remove some data that is underrepresented, like the mode 4 and mode 5, this saving mode, and also the load for cell 2 and cell 3. And the third step is a generated configuration groups. So something like this, these two will become to the same group because they have identical configurations. Of course, one group can have multiple stations. So after the grouping, we found there are totally 84 unique groups. And the last step I did is I pseudo label two test stations of type 11 and one test station of type 12 by analytic models. I'll talk about it at the last. So now for the tree-based algorithm, what the input features? I want to keep it simple, so no any historical feature data is used. So we can basically put out, there are 27 features totally. We can put them to like 4 categories. This first one is like a load and energy saving mode. Yeah, basically the load and the saving mode. And the station configurations, like RU type, how many number of the cells, and the style antennas, this combination of antennas, text power, such, and also the time, hour and day. The last is the spectral configuration. The first one is configuration group I already talked about, is like 84 groups we have. Now the station ID. This station ID is sort of handle the situation like the hidden factors for each station. So we can use something like embeddings or encoding for station ID. But I like what about daily average load? But I think that may have the risk of introduce future data. So what I did, I just simply cut the station ID to categoricals. So that's all the features I use. So to handle the situation like unseen stations and the seen stations, I separate the models. So first of all, this is the score achieved, public and private. For the seen stations, I use all the 27 features, but for the unseen stations, only 25, because the configuration group doesn't make any sense because you don't share any similar configurations in the trained dataset. Also, the station ID has to be dropped because it's unseen. For the trained data I use is for the seen stations without these two outliers, this type 11 and type 12. And for the unseen test station, of course, I use all and plug those three test stations I pseudo-labeled. And the most important features, they are separate because for the seen stations, they are configuration group and station ID. These are top two because, as I said, there's some sort of a individual level, station level configuration, so which can be specified by the configure ID, station ID, and also the configuration group. And something others like the load and RU type. And for the unseen station, if you treat the model, the top one is RU type and the load. And now you will see the antennas like text power, they showed up because there's configuration belongs. Okay. Now let's talk about how I pseudo-label type 11 with analytic models. The first thing I found is that for type 11, although it's brand new, but it's basic configurations in terms of the text power, frequency, band, they're pretty much similar to type 10. So let's just do a study on the type 10. So this is the type 10. Type 10 only has one cell, only cell 0. So we plot cell 0 load versus energy. We can pretty much see some good observation. First one is pretty much their linear relationship, right? The next one is we can sort of see two different lines. This is blue and orange. I separate them already because they can separate by the text power. Actually, you can see use different text power, use different line. The next observation is around the load 0.1. There are actually for each text power, there are separate lines. Let's just focus on the orange. So there is this line and that line. I call it mode 1 and mode 2. I guess below 0.1, maybe the station is in some sort of a dormant state. So it responds like this. But if the load is above 0.1, it becomes more active. So the relationship becomes this line. So this is a good observation. Now let's talk about the type 11. The type 11 only have one data point, as I said. So this is a data point. So this point is actually very useful. It gives us a hint of the response of type 11, because type 11 also has a text power of this orange of 8.03, 8.04, and it just goes on this line. So what I did is just assume the type 11 in the active mode will respond like this line, and in the dormant state respond like this line. So this is the one I pick. It's actually 835. You can see the load is, I also timed 100. So for this one, it's almost in the active mode because it's above 10. So basically about 0.1 here. So based on this linear regression line, we can feed a new energy line. You can see I got a new energy line. And then I pick another type 11 because this one is more like in the dormant state. They are below 10, which is below 0.1 here. So from the energy, we can get, from the load, we can get an energy line. So I feel this too for the type 11. So yeah, that is for the type 11. For the type 12, pretty much similar thing. We have to pseudo label, but differently. because
1 minute to finish.
Okay, thank you. But type 12, they are using some new configuration like antennas with 64. And this is the sharp analysis on the ANSI station. We can see that other than the load and the RU type, now the most important feature is antennas and the text power. And when this feature is greater and the energy consumption will be increased, it makes sense, right? We have more antennas and text power than it is. So we did a study on antennas or the impact of antennas, because antennas they are in the two of power something 2, 4, 8. So you can see the two examples like this one and that one. Basically, suppose other configurations are similar. If you double the number of antennas, most likely this slope will double if you do a linear regression. So that's the observation. So what I did now is just also based on 10, because 10 is also similar to top 12, but because type 10 has 32 antennas. Now I just fit this line and basically double the slope, and then we can get a new line of the of energy. So I feel this type 12 observations with this load 100, and then I feel this energy. So yeah, that's it. Thank you.
Thank you so much. Right now, let's go into Q&A with Nicola and Vishnu.
Hi, Ning, and thank you for the very nice and in-depth presentation. So if I understand correctly, you have these two models. One is more general and for base station that you didn't see before. So this model is more relying on the cell load, for example, and others that are more for the base station that are in your training data. And my question is, do you feel there is any possible direction to have even better performance in your models? So do you foresee a future direction? And do you feel that you may have done better if you had some particular information that is not available? So, for example, in the previous presentation, someone was mentioning the finer granularity data. Do you think that there is some information that it may allow to have more accurate models?
I think two parts. First one is, of course, if we have more data, it will generally increase performance. But no matter what kind of algorithm you use, like GBM or DN, that's fine. Because as I said, there's something should be hidden. It is not available in the data set. Another thing I want to answer is there's other approach as well, because we can extend these analytic models, including more data, and also introduce more statics models. Like we can specify what kind of parameters is expected, given some certain antennas, given certain text power. So it's kind of brand new approach, but it could have potentials. Does that answer this question?
Yes, thank you so much. Please, Vishnu.
Thank you very much. Again, I agree with Nicola that your last analysis is very interesting. And can you tell us a little bit about the type of model that you used again, please? What is the type of model that you used?
That model is just the basic land GBM using those 27 features. Yes, but as I said, for the ANSI station, I pseudo-label some. So basically, I increase some sample size. I manipulate the data perspective. In terms of modeling, I took the approach of a data-centric way. I want to improve the data first, and then using simple models. That's what I did.
Very interesting approach. Okay. Can I ask maybe one more question? The hourly data, hourly information that you have for the power, do you think that is useful at all? Because many participants you saw are using that type of data, that type of feature. So is that useful for you, or did you find that it's useful at all?
Hourly data. What do you mean by hourly data? So
the transmit power based on the hour of day.
The load, this load is hour level, right? So this load is of course is very interesting. It is very useful, But if I can make it complicated, like using historical or whatever, but I think the focus here is not like a prediction. It's like the study the configuration from configuration perspective, how it impact the consumption, right? So I didn't do too much feature engineering. So you can see this very basic features. Yeah.
Okay, thank you very much.
Thank you.
Okay, thank you so much. So these were all our presentations for today. But before we close, I would like to open for general questions. So I understand that other participants, other teams. Can you stop screen share? Ning, can you stop sharing screen?
Sorry, you want
Can you
me?
stop? Yeah, screen
Oh, you
sharing.
want me? Oh, okay, okay. Sorry. Yeah, yeah. Just a second. Yeah.
Can you stop?
Okay. Yeah.
Okay, thank you so much. So I would like to open the floor to other participants to ask each other questions. So we have like roughly 7 minutes for questions. So anyone you can switch on your camera and pose the question to the other team member. This is quite an interesting time to learn what others have been doing as well and how we can improve. Any question? No?
So I have not read Isaac's code, but in the chat I saw one question stating that Isaac has done some post processing by adding 15 to the energy value. So this post processing step, was this done? Did you observe that your model was under predicting the energy values, and that is why this was done? And how was the number 15 selected?
Okay, thank you, Chris. So when we see the three base model, high level, unseen, high level. So if we use a deep learning fit well on the unseen data, especially in higher value. So three base model cannot predict that level because we had more than 32 antennas, and the bandwidth has had more than others real life. So 15 was just using a proven public leaderboard. I used a 15 to add.
Understood. So 15 was basically empirically derived, and this was because you were getting better results on the public leaderboard with this process.
Anyone else with some questions?
Yes, I would have some question to Ninja. Hello, Ninja. My question is, as you explained, you are trying to, split, the different base station with different models. Like in some model, you simply use 100 times, the features, or in some way you use the seen and unseen. My question is, how do you get some specific base stations? I mean, such intuition. How do you get such intuition?
Tuition, I just do deep exploration on the data side. Yeah, I found they are just have different configurations, and yeah, I have some assumptions, and then I explore the data and then try to verify my assumptions. If it's not right, I have new assumptions. Yeah, just exploration. Yeah.
Okay. Okay.
Thank you.
Any other questions? Okay, so how convinced are we that future values were not used? Nicola?
From our side, we received the code from all the participants and we are checking it. We mostly finished to check it. So we are making sure, of course, that no future values were used. And also, I think the participant that presented today, they did a good job also in explaining that they did not use any future values to improve the performance, but that they just relied on some historical information like looking into the previous 3 hours. Somebody was looking into the previous 5 or 6 days. So this is my answer.
Thank you. And maybe some quick comments. I would ask maybe a few participants, Raphael, Licheng, Julius, Krishna. Your experience in this competition, how was it, and what do you think about your results and your solution?
So, okay, I can start with the question. And so this, for me personally, this was the only competition in the last maybe 1 or 2 years where in a tabular setup, because of the way the problem was formulated, a neural network was outperforming the boosting models. So so that construct itself was very exciting for me, and exploring ANN models on the tabular data, that was very nice. And also I had an opportunity to read the research paper, and and coincidentally I read the research paper after I implemented the ANN. So I was very happy that the same model was used in the earlier paper.
Okay. Raphael, Licheng, any comments? Julius? Oh, Raphael.
Sorry. Hi. So responded the answer. For me, it's very nice to participate in a much learning in this competition, and seeing the others what we do, what they do. I think is a great opportunity for learning, and I have much more ideas to win this competition now, but okay, that's fine. I just glad to participate, and that's it. Nice, thanks.
Thank you. Licheng?
Yes, for my point of view, I think I did learn a lot. I think, yes, the data is good, but, the only thing is, for the test data, because we don't know the W, I think that would be a problem. That is the weight. I mean, we know the weight, but we don't know how to update the weight. This is the thing I think maybe we can do as a Kaggle. Maybe we have a background to test it. Also, the configuration can be also unknown because we can see some participant use the data from the test site. I think this is not that not that realistic, because test data always cannot be used. We see some competitor use these like features as whatever input, or they do some experiment on this one. I think this is not really realistic. For others, I think I learned a lot, especially like the seasonality of the features and how to handling the things in different noise level. And also one more thing I think inspire me is a lot of competitor use the artificial neural network. Before I thought because of the missing artificial neural network would be worse, but finally it seems it works really good. And also maybe LSTM and other time series maybe also have a good performance. So all in all, I think everything is really good for me.
Okay, thank you. Julius?
Thank you so much. I think this competition was interesting from the metrics. We were to be evaluated using mean absolute error at the beginning, and then later on after the close of the competition, WMAP for the final leaderboard score. So I think that was very interesting because it ensured we are not probing the maybe probing the leaderboard so much. But something I noted is that my best scores in while at the first part of the competition, that is those that were being evaluated using mean absolute error. They still turned out to be the best when the other metric was used. So I really went a lot of extra miles trying to split the data to look exactly like to split the training data to look exactly like the test data that was missing some base station. But that still did not work out nicely. So I believe it was an interesting competition in that dimension of the metrics used and every other thing. So there was a lot of anxiety about the leaderboard. It kept on shifting and changing. So I guess I've learned a lot even from the solutions, and it was quite interesting. Thank you.
Hey, thank you so much. So everyone, we thank you so much for putting much time and effort. I know the leaderboard kept on changing, and yeah, there was stiff competition until the end. It was really a nice learning point for us as well as organizers. So we hope next year we can do better. But I think we have tried to be fair. And of course, we will check the code, the reports, and the presentation today. We will put everything into consideration when giving the final score. So hopefully we can manage to seal the leaderboard next week. But the final winners will be announced, as I already pointed out, on 2 December. So we still have a month or so to go to announce the final winners. Final remarks, 1 minute, Nicola, and I would ask Vishnu to close.
Thank you, Thomas. So I want to thank all the people that participated. It was very nice to see the many participants. It was also very nice to see the many discussion on Zindi with the question and answer on how to tackle this problem. So there was a lot of interest, and it was nice to see and to try to help when needed. And also, I'm happy that today we have seen many solutions and very different approaches. So someone was more into gradient boosting, others on neural networks. We have seen some combination of different models, so a very diverse set of solutions. I think this is very good. And as Thomas said, we will evaluate all the material that you have sent, so the code, the report, and this presentation. And soon we will communicate the winner of this competition. I hope in the future there will be more opportunities for us to collaborate and to launch other challenges, always to tackle real-world problems. So I leave the floor with Vishnu, and thank you again.
Thank you very much, Nicola. And yeah, I remember our initial discussions to launch this problem statement. Your commitment, thank you very much. It's absolutely fantastic problem statement, data set. It's very exciting set of solutions. Look at the set of solutions. I think this is really exciting. There is a varied range of solutions, and I am very excited to say that some of you have really gone into the details of it, looked at problem research papers. I can see at least 2-3 research papers being referred here. Thank you very much. That's very exciting as well. I think the prices are really good. Dubai is calling. Let's see how that goes. And I believe that the competition is very close. Feature engineering is very interesting for me personally. The feature engineering part was very interesting because I claim to be domain expert. But yeah, it was very interesting. So yeah, thank you very much. And it's very exciting problem statement. We look forward to the results. All the best to all of you. They keep your toes and fingers crossed. Thank you very much. And we are closing now. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.